we have stress strain relationship given by this thing where epsilon 33 is 0, 1, 3, 2, 3 are 0, sigma 1, 3, 2, 3 are 0, but not epsilon 3, 3, sigma 3, 3. So this is the plane strain condition. So both the things we can write accordingly as simply in this manner. So sigma is D matrix times epsilon. So depending upon the plane stress, plane strain, the D is used. If it is plane strain problem, you use this as your D matrix. This as the D matrix. If it is plane strain condition, plane stress condition, then you use this as your D matrix. Plane stress, including this coefficient. So this together is your D matrix, and for the this one for the plane strain, this guy is your D matrix. So that means we can represent our stress strain in the in-plane stresses like sigma 1 1, sigma 2 2, sigma 1 2 with respect to epsilon 1 1, epsilon 1 2, epsilon 2 2 using this relationship. And further constitutive matrix, since this relationship is constitutive relationships. So further, so since sigma is written as, but our epsilon is given by B times U. So using this approximation, when you put down in the principle of virtual work, what we derived for the equilibrium condition was that K times U is equals to F, where K is given by integral B transpose D B dV, and this force vector is sum of body forces plus traction forces. Which was represented as integral omega, so n transpose B dV, whereas the tractional forces is, this integral is with respect to surface integral, so n transpose tractional forces times dA. So this is how the F is obtained, and U is the degrees of freedom or the nodal degrees of freedom, which is D1 to D8 for the given element. And based on that, since if we know our shape functions and the gradient of shape functions, which is related by the strain displacement matrix B, and if you know your constitutive relation D, then we can obtain our K matrix and the nodal vector, nodal force vectors. Then what we'll do is we'll carry out the assembly and then impose the kinematic boundary condition and condense the K global to determine the unknown degrees of freedom, and that's how we solve the problem, just as we have seen the in the one-dimensional problem. Now, yesterday we have shown some values of n and b for a regular quad with a regular quad as well as a constant strain triangle. Later we also discussed about So we checked for the formulation for a quad and then for a triangle, and we showed that for a triangle the strain is constant, and we talked about its behavior, and hence we used to call it as constant strain triangle for the triangular elements. And that constant strain triangles are bad when you're doing if you have only one element on the depth of the beam. So it is generally recommended that if you have more than three elements, it would reasonably approximate your exact field. But if you have only one element along the depth of the beam, since the axial strains are zero through the finite element, whereas the axial strains are non-zero for an exact thing, and vice versa for the shear strain. So we also, that's what we discussed in the previous class. In today's class, what we'll do is uh, we will try to extend this problem for the axisymmetric case. The reason is the entire formulation remains same with only minor kind of changes. So in today's class, let's deal with the axisymmetric problems. So now, so these set of problems are the problems where it is not all kind of problems. There are certain restrictions to solve this axisymmetric problems. First thing is the body. The body or the structure is generated. For example, if you have the structure such that it is obtained by the uh, rotation of a plane about an axis. It can be any plane. Here I might have just drawn a rectangular shape. It can be any shape, the cross section. And if this is the axis of rotation, then you would generate something like with this as an axis, a small kind of a cylinder of depth, let's say of depth h. Okay, it would be something like this. I mean, I may not be drawing it good, but this is axisymmetric, so it has to be perfect revolution. So and similarly the downwards will also have the same thing. So you will see it's like I mean, it's difficult to draw, but it's kind of a small cylindrical a small cylinder with the circular base. That's what I have driven with a height h. Okay, so now so these so if you have certain area dA, and if the dA is rotated about this axis of rotation and the body is formed in that, then these are called solids of revolution. So the structure should be, first thing is obtained by structure should be obtained by revolution, or also known as, these are solids of revolution. That means you take an area and sweep it about an axis. The net thing that forms is your structure. And this is the first criteria. The second criteria are the loads should also be axisymmetric. Axisymmetric means it should be independent of theta. That means if let's say if this is angular thing I'm measuring, this cross section is same as this cross section is same as this cross section, any cross section, this because each one has a different theta, so all the things should be in same. So similarly, the loads applied at any given cross section should also be independent of theta. When somebody says axisymmetric, it says that independent of theta. Now further, the loads, the structure, the loads, then boundary conditions. The boundary conditions should also be axisymmetric, that is independent of theta. Then material should also be axisymmetric. For example, if I take this thing, the best choice of axisymmetry is isotropy, but not necessarily we are restricted to isotropy. We can even deal with other less symmetric materials also, provided the principal directions. For example, if I take this kind of a small area at this place, so let me do something like this. I'll cut a line, I'll cut this thing along this axis. So let me see about, let me draw this thing. If I'm looking at this direction, so it would look like C D C dash D dash. So if the material has material principal directions, and it's that so let's say if this is your material principal directions, let's say this is y dash and x dash, and once you rotate it, right, this will become y dash x dash because it has rotated by 180 degrees. So that is, if your material principal direction is independent of theta, then also you can take those materials. So it is not just restricted to isotropy, but also to the kind of class of materials where material principal direction is independent of theta. For example, if you take orthotropy and such that its directions are maintained in this plane of rotation in this manner, which is independent of theta, then also your material is suitable. Now, when I say boundary conditions, the boundary condition further can be classified here into kinematic boundary conditions or constraints or displacement constraints, and the other things are natural boundary conditions, which are nothing but loads. So loads also, all these both the things has to be axisymmetric. So sometimes we can also handle non-axisymmetric loads, that is also there, that I will explain it at the end of things. If we have such kind of non-axisymmetric loading, how to deal with it can also be used with this axisymmetric formulation. The main reason for going for an axisymmetric formulation is the reason that if you want to solve this entire problem as a three-dimensional, it would be numerically expensive. While if you do it as a planar things with taking into due consideration of the symmetries, then you're solving the same problem within less complexity. So that means if you try to solve the problem entirely without considering the symmetries, it may run for, let's say, 3 hours because of the size of the problem. In the other way around, if you use this axisymmetric formulation, maybe you can solve the same problem with the within, let's say, a 10 minutes or so, because the one dimension we are reducing it, and hence the number of, I mean, I'm just giving an example. It would also vary from one problem to other problem, but you can reduce your complexity drastically from 3D to 2D, and your solution is exact. It is not that you are approximating it by doing a by not solving it in 3D and solving it in axisymmetry. This axisymmetry is only a formulation that will still get you the same approximation as you would have done with a 3D kind of stuff. So it's only a reduction based on the symmetry rather than an artifact. So, or an approximation. So with that as a consideration, let us see how the axisymmetric formulation would be carried out. So since we have seen in the axisymmetric, our coordinate systems are not XYZ. XYZ are Cartesian, whereas in axisymmetric we have clearly seen that there is a radial position and a theta, and the axis itself is z. So it is better sometimes to write equations in r, theta, z. So in kind of axisymmetric problems, we will try to use cylindrical coordinate system like this r theta z rather than Cartesian system, and hence our equilibrium equation, even though it is the same, has to be rewritten in terms of r theta z. So the same as your restraint relationship, strain displacement relationship, even though the equilibrium equation remains the same, but the terms in it would change. So it is like telling the same thing in two different languages, but the meaning would be, or the net thing what you're solving is the same. So what we'll do is we will not try to solve it from the principle of virtual work, since we have already seen that all the forms are remain same, that we are rest assured that our equilibrium equation, even in the axisymmetric, would be of the form as k u is equals to f. Only that our u's are not based on Cartesian, but they are based on r theta z, that is ur, u theta, and uz. Right? Similarly, these things also depend upon the formula, the things. And further, since we are only trying to analyze only one cross section, so we have only limited to not all strain components or the displacement things. Very few things are required, so that we will express it by using the asterisk relationship for the axisymmetric case in a while. But I'm just bringing it the similarity that what we need to be done, and the k will be still the same It is integral B transpose dB. This would not change. The only thing is B, D and B are expressed for in terms of axisymmetric notation rather than the Cartesian notation which we have seen. So first let me give you the stress strain relationship for the axisymmetry. In the axisymmetric cases, since the problem, let's say we have 3 degrees of U, V and W for the Cartesian. In this case, we'll call all these things as UV. However, we mean that U is UR, V means theta, and W means UZ. So I will still retain UVW formulation notation, but when I say in current problem UR means it is displacement in the radial direction, U theta is in the circumferential this is circumferential direction, this is in the axial direction or the axis of rotation or the z direction. So for this, what we'll do is, let us since it is axisymmetry, the displacement v has to be 0. It has to be independent of theta, means u theta has to be 0, and because of that we can directly write our tau r theta is equals to 0 and tau theta z is equals to 0, and hence also gamma r theta is equals to 0, gamma theta z has to be equals to 0. So out of 9 stress strain components, we already knocked off the 4 things, and hence we will only end up with the remaining 5, out of which tau rz is equals to tau zr. That means we have only 4 independent stress components and the strain components that are there. So let me write those 4 independent things. Those are sigma rr, which we simply call it as sigma r, sigma theta, sigma z, tau rc is equals to d times, let me call it as AS. DAS means D for the axisymmetric case, which is different from the plane stress or the plane strain which we have seen earlier. So this is epsilon r, epsilon theta, epsilon z, and epsilon gamma rz. Gamma is an engineering shear strain, whereas epsilon is the normal shear strain. Now, where our D matrix would be symmetric and it is given by, let's say, E11, E12, E13, E14, E22, E23, E24, E33, E34, and E44. This is symmetric by definition. Further, this even through all these coefficients will be varying depending upon the material symmetries. The material symmetries with the full symmetry is isotropy, with further less is orthotropy, or generally anisotropic. So depending upon whatever is this, these coefficient would change. However, in this class we will restrict ourselves to an isotropic case, in the case of an isotropy, we can represent our D matrix simply by this relationship. So the D matrix for the axisymmetric and isotropic material is represented by following. Where F is given by mu by 1 minus mu and G is given by 1 minus 2 mu by 2 into 1 minus mu. So this is so since it is isotropic material, we should only have two independent material constants, E and mu. So if you look at it, it is defined by E and mu. Even F and G are only restricted to mu, which is part of the two material constant. So for the isotropic case, for the D and the D matrix for the axisymmetric is defined by the same thing, but by this thing. Unlike the D matrix for the plane strain and plane stress, which look little bit different. So this was the D matrix for the plane strain, and this was the D matrix for the plane stress. So and further, you see it is 3 by 3 and 3 by 3 in this plane stress and plane strain cases. However, in the plane in the axisymmetric, this is a 4 cross 4 matrix because we have four relationships here, which is sigma r, sigma theta, sigma z, and tau rz. Okay, which are related to correspondingly epsilon r, epsilon theta, epsilon z, and gamma rz. Okay. Further, the strain displacement relationships can be written as epsilon r is dou u by dou r. Simply write it as u gamma r, and epsilon z is given by dou w by dou z. These are not that difficult. Next, gamma rz is u, that is u comma z, plus w comma r is the thing that is left. But when it comes to epsilon theta, this you can use it from the same definitions what we have used for the Cartesian. However, for epsilon theta, I will give you a physical meaning. So let us say that we have an initial circle of radius r, and under the whatever the conditions, under the due to the deformations, it has elongated to a radius of r plus u. So let us see now the epsilon theta theta direction would be is 2 pi r plus u minus its initial circumference was 2 pi r, and the new circumference is 2 pi r plus u divided by 2 pi r would give you u by r. So epsilon theta is given as u by r, which is quite understanding that because of increase in the radius, you experience a hoop strain epsilon theta, which is equals to u by r. Based on what we did was we just used the definition of strain, deformed length minus original length divided by the original length. So deformed length is deformed circumferences is 2 pi r plus u, and the original thing was 2 pi r divided by 2 pi r, which would give you u by r. So this is our the relation which we call it as stress strain displacement relationships. for axisymmetry. So now we just want to write this in a manner such that it is equals to epsilon times uh, first let's express it as an operator form, some dou times u, and there is no v because v is equals to 0, which we already said. So we have only two displacement, which is this thing. So where our dou, the operator matrix, can be defined as epsilon r, epsilon theta, epsilon z, gamma r z. It is only with respect to r, so it is dou by dou r, and there is no w component for epsilon r, so this is 0. And so this into this will be dou u by dou r. This is the definition. And this one is 1 over r because u is already there, 1 over r, 0. Next one is 0 dou by dou z, and this one is dou by dou z, and this one is dou by dou r. So our operator dou can be written as dou by dou r 0, 1 over r 0, 0 dou by dou z, dou by dou z, dou by dou r, which will relate our uv to the displacement epsilon r, epsilon theta, epsilon z, and gamma rz in this manner. Okay, so this operator relationship is little bit different than what we generally see in the Cartesian format. Okay, so anyway, since we remember this, so now what we need to do is we need to obtain our strain displacement matrix. Our strain displacement matrix can be obtained in the fashion that, but we want our epsilon not just in an actual uv, but we don't want just uv, we want uv at the nodal coordinates. So that is the definition of it. So then what you will do is, for this uv has to be used as a operator notation, so as an approximation. So we know that our u and w, each one has to be based on the shape functions times our capital U. Our capital U in this case can be defined as u1, w1 at node 1, u at node 2, w at the node 2, u at node 3, w at node 3, u at node 4, w at the node 4. Because if you look at it, I'm just drawing for a let's say simple quad kind of things for an axisymmetric element. Okay, this is the axis, and this is kind of my quad. So if I'm kind of developing for such kind of thing, these are my nodes 1, 2, 3, 4, and accordingly I have UW, UW, UW at all the 4 places. So this is also your degree of freedom 1, U1, W1, U2, W2, U3, W3, U4, W4, or alternatively we can call this one as degree of freedom 1, degree of freedom 2, degree of freedom 3, degree of freedom 4, degree of freedom 5, degree of freedom 6, degree of freedom 7, degree of freedom 8. This just looks like our plane stress or plane strain element. However, it has a distance which is measured from the axis. Anyway, we'll come to that. So if I take this fellow, which is u and v, a generic expression of displacement at any point u and w and substitute back in this relationship. So then my epsilon, which is equals to dou times uv, and uv is this thing, so I write it as dou times n trans, sorry, there is no transpose, I don't know why I have put this transpose, n times u, so it is n times u. So where n, as we saw earlier, it is n1 0, n2 0, n3 0, n4 0, 0, n1 0, n2 0, n3 and 0, n4. So the same n times this u. So this together will form our B matrix or the strain displacement matrix. So we can state that our this operator matrix times n would be our B matrix, because we know that the dou matrix is 4 cross 2 and this one is 2 cross 4, and obviously our B matrix is 4 cross 4. So with this, what we can do is, on simplification, one can show that, so we can as well as do ourselves. So dou by dou r 0, 1 over r 0, 0, dou by dou z, dou by dou z, dou by dou r, so we just take this and multiply with this times that, this time, so on like that. What we'll get is dou n1 by dou r, um, zero n3 by r 0. So this is 0. This fellow with this one will give you dou n1 by dou c. And the fourth one would give you this would give you only this one existent. So 2 by dou z, dou n2 by dou r, dou n 3 by dou z, dou n 3 by dou r, dou n 4 by dou z, dou n 4 by dou r. This is the way one can do it, or simply let's just leave it in this fashion. But let us also further, depending upon the coordinate system, how we use it, these are further again classified. This has to be a little bit changed. Let us see how that is there. So anyway, let us look at this element much closely by kind of uh, expanding it or exploding it. So let's take this as our element. Let's say this is our x and this is our y. This is a local. This is only the local things. However, our global things are, this is our r, sorry, z axis, which is also known as axis of revolution, about which we have our things rotated, and we have a radius of, let's say, this is the radial direction. So let us take an element which has a dimension of let's say this is and this has a dimension of b. So in the local coordinate system, we can write the coordinates as same as what we have done, which is a comma b minus a comma minus b, a comma minus b minus a comma b with respect to the local coordinates y and x. Okay, so but we know that the center of that is the Rm. So let this be the Rm, and in that case, and if we are measuring R, we know that our R is nothing but your x is measured from this Rm. So this is Rm plus x, or you can rewrite it this one as x is equals to r minus rm. So, and hence your B matrix can be rewritten or the dou matrix, which was defined in the global coordinates as dou by dou r 0 1 over r 0 0 dou by dou z 0 dou by dou by dou z dou by dou r. Now our local y is our z direction, so we can say that dou x is equals to dou r and dou y is equals to dou z. So based on that, I can rewrite this phi in terms of local coordinates y and x as dou by dou x 0 1 over our r is written as x plus rm. So this is x plus rm. So this is That means when you are measuring from respect to x and I mean, even though you have your local coordinate system, the element location from the axis do matters. So that is the reason this rm plays into the picture. So each element would have a different rm depending upon an element which is sitting here would have a different rm compared to an element what we have seen. So each element would have different rms, so that would also come into the picture, even though the x, all the other things will still remain as it is. So this is dou y, this is, so if you want to use this dou operator in the local, you can use it in this manner. If you want to use with respect to global coordinate system, the global coordinate system is r theta z, and the local coordinate system is x and y, only provided that your rm is also measured from this global set. Okay, so you also need an rm, but yeah, the x and y is sufficient to kind of use this. So this is your way to represent it. So but we know that if I represent in this manner, if I represent in this manner, my shape functions are already known to me. Let me get you the shape functions from the previous class. Known that this is x and y, our shape functions are given by the same thing. So this element shape functions is same as this element now. So the shape functions are these things, and so further we can see that um, dou n by dou x and all other things remain same, which we have found in the last class. So now here when you multiply it, your B matrix, which would look like in this global coordinate system, which was looking in this, in the global coordinate system. Now look, very simple. In this is part of the global. This is in the global coordinate system. Now would look in the local coordinate system would look like it's the same thing, but you are expressing in different coordinate system. So this is dou n1 by dou x, 0 dou n2 by dou x, 0 dou n3 by dou x, 0 dou n4 by dou x, 0 n1 by x plus rm. That is the only difference, 0 n2 by x plus rm, 0 in 3 x plus rm 0 and 4 by x plus rm 0 0 dou n by dou y 0 dou n2 by dou y 0 dou n3 by dou y 0 dou n, this is 3 dou n4 by dou y, and this is dou n1 by dou y dou n1 by dou x dou n2 by dou y dou n2 by dou x dou n3 by dou y dou n4 by dou x, sorry, dou n3 by dou x dou n4 by dou y. This is our V matrix for the axisymmetric. Either you can, since why we have represented this, because we know our shape functions and its derivative with respect to x comma y. So this was the same element, same things which we have obtained in the previous case for the plane stress and plane strain. The same thing has been used here as well, except that our B matrix has a little bit different shape and size and entries compared to plane stress or a plane strain condition. Okay, now we have B, we have our D matrix for the axisymmetric. So then we are ready to compute our K matrix. So this is so now let me write it, our K matrix. So since you know all the entries here, so you could, you know the entries of it, you know n's, you know dou n by dou x, so you can compute each and every entry of it and keep it here, find the transpose, put it here, from the above get the D matrix, put it here, again take this B matrix, put it here, multiply it and integrate with respect to dV. Now what is dV? dV is nothing but in this case is r d theta dr and dc. This is the circumferential direction, this is the radial direction, and this is the axis direction, axial direction. So dv is nothing but your r d theta into into d theta into dr. So this is how you compute your volume in a cylindrical coordinate system. So that's what we have shown here. So I mean the easiest way to do is so let's assume this is r d theta, this is dr, this is dc, and assuming it's a small cube, you can write it as r d theta dr into dc. So that's how you get your things. So you know all these entries and you can compute it. So and we know dr dz can be represented as x d theta dx dy in this case. So I will represent by using the same notation, b transpose d b, sorry, this is not this is still r, so this is x plus rm d theta dx dy. So and if you integrate it now for the, you can replace this volume integral by three integrals where theta varies from 0 to 2 pi, radial varies from 0 to r, and let's say y would be from 0 to h is the height of the cylinder. So in this manner your integrals has to be computed. So let's since we have given this template form, which like yesterday we could use it in either manually or using some symbolic processor like MATLAB or a Mathematica and integrate it after computing B transpose TB, and hence you get the kind of stiffness matrix. Now let us also have a look at, now we know the displacement vector u, which is nothing but u r u theta w and sorry, since we don't have u theta for axisymmetric, so our u matrix u vector is nothing but u1 w1 u2 w2, which is like radial displacement, axial displacement, radial displacement, axial at the different nodes. Similarly, let us compute the force vectors. Okay. The force vectors also consists of uh, the radial force F, which is the radial thing, and we have our theta direction, which is there is no circumferential loading, and then we'll have axial loading fz, and the so your force vector, which is obtained by the body forces and the tractional forces. So let us say these are our body forces along the uh, the radial directions and along the thing, and so we should not actually represent like this. So let us say the body forces are given by Fr and Fc. There is no F theta because it's the body, the loads are also has to be independent of theta, so F theta is by default 0. So so let me just write it this as Fr and Fc, just like I have written U and W. So we have only Fr and Fc, and our tractional forces are again, let's say Tr and T theta. Sorry, Tz is the tractional forces. So our F body force, total F body forces, is obtained by integral of volume n transpose Fr F theta dV. Again, dV is replaced by R Rm plus X into dx d theta dx dy, and your F tractional forces is given by gamma gamma times the n transpose dA. Okay, so this would be a little bit different. Here this, let's say if it is acting on an external surface, then we know that dA comprises of r d theta into dz. Okay, that would be our area on the thing. So this can be replaced as x plus rm d theta dz. So this would be a double integral with 0 to 2 pi uh, n transpose, sorry, this, there is a traction vector t x plus r d theta dz, 0 to whatever is the height. So this can be further replaced by 0 to 2 pi, 0 to r, 0 to h in transpose F, which is body forces, times Rm plus x d theta dx dy, and this one is not dy dz. I have to replace it with, this is in the local coordinates, it has to be dy. So our total force vector, this is frf. So our total F is nothing but sum of body forces, plus sum of the traction forces. So now what we have done is, I have determined how to do K matrix, and we know our U, and then I have also showed how to obtain the nodal RHS vector or force vector. So then in the axisymmetric problems, we have completely defined at this given point how to obtain the K matrix, how to obtain F matrix for the given loading, and hence what happens is we are in a state very much similar to that of the plane stress and plane strain condition, except the formulation is little bit, I mean the B, D and F matrices, how they look like is little bit different from that of the previous class. Otherwise it is most similar compared to the previous thing, and hence if we can develop element stiffness for one single element, we are as well as can repeat it for all the elements, do the assembly, and then impose the kinematic boundary conditions and condense the KUU matrix and solve the global condensed matrix for the unknown degrees of freedom. Once you determine the unknown degrees of freedom, then you can wholly determine the displacement and the stress strain field all over the body. And in fact, in some of the commercial software, once you obtain the solution, they also have a feature where they will also generate the same solution by revolving itself with the axis. So you can even visualize the solution which you obtained in a single plane is same at any given plane. So they revolve that solution across the axis of rotation to see a 3D kind of a feature, even though you might have solved the problem with the 2D axisymmetric nature. So this is how you solve your axisymmetric problems when your material is axisymmetric, load is axisymmetric, boundary condition is axisymmetric, and the structure is obtained by the solid of revolution. Now, as I promised earlier, maybe I'll stop at this given point and just check if you have any questions, and then I will deal with a special topic, which should be how to deal with the non-axisymmetric loads for the axisymmetric structures. So any given function phi can be expanded in the trigonometric basis as so. If you have this thing, and we already know that our um, this Fourier basis, which is cos n theta sin n theta, are orthogonal in nature. That is, the properties of Fourier basis are such that integral minus pi to pi sin m theta sin n theta is equals to pi times delta mn. That is, when m is equals to n, delta mn is equals to 1. If m not equals to n, delta mn is equals to 0. Further, not only this, further we have another two things, that is cos m theta sin m theta, sorry, let me put it cos first. Cos n theta is also given by, it's only thing, it is 2 pi delta mn, and minus pi 2 pi cos m theta sin n theta is always 0 because their cos and sine are orthogonal to each other. Okay, so because of this orthogonality, what we can do, if we integrate this function phi with respect to d theta minus pi to plus pi, what will end up is getting 2 pi a naught. At the same time, if I integrate minus pi to pi phi cos n theta d theta, I would get pi a n. And similarly, if I integrate minus pi to pi phi sin n theta d theta, I would get so. I think this I have made it wrong. This guy is still pi delta n. So by this feature, we can determine our projections a and bn. So that means I can say that my an is given by integral minus pi to pi 1 by pi phi cos n theta d theta, and my bn is given by 1 by pi minus pi phi sin n theta d theta, and my a naught is 1 by 2 pi minus pi to pi phi d theta. So this is how we could project we can get the projections of our all the basis of all the basis vectors. So That means any given function can be represented as a series function in terms of cos and theta, and those projections are obtained through this function, through this computations. Further, so since we have this kind of thing, what we will use is we'll use this solution to compute our non-axisymmetric loading. So let's say for if you have a set of loads which are FR and FZ, which are non-axisymmetric, or we can as well as have our TR and TZ. These are which are non-axisymmetric body forces, or which are non-axisymmetric traction forces. So in these cases, what we'll do is we will kind of project them into the basis vector, and then using the principle of superposition, we'll obtain it. The principle of superposition says that by the same thing, so what we'll do is any given body force or attraction force can be split into corresponding projections, this thing times the cos n theta and sin theta. Further, I just want to remind you that this is the symmetric part. These are the symmetric part of the expansion, and these are the anti-symmetric part of the expansions. So this is because it is sin theta, it is anti-symmetric. Cos theta are symmetric in nature, so obviously ANs are the symmetric part and BN are the symmetric part. So if you have a loading which consists of both symmetric parts and the anti-symmetric parts, we will just divide them according to the basis vector. Let's say if, I mean, not necessarily to infinite series, because our given loading can only depending upon certain basis vector. It may not have projection in all the basis vectors. So let's say if it has it's in certain only for certain combination of n, then we can individually compute the solution in those things, in those corresponding stuff, and then multiply with corresponding basis vector and superpose it in the given fashion. So that means, let me show you out that, for example, if you have these combinations which are like FR, FC, TR, TC as your total loading, that can be again computed as uh, that can be computed as FR bar, FC bar, TR bar as the projection of nth component, and of the nth component, that means, or as well as I could write it as n here. Since these are only symmetric part, we'll only deal with the symmetric parts. If only if you have anti-symmetric components, that the anti-symmetric component would be f theta, and d theta, that would be summation of Now, if you have these components, then what you do is you find the solution for one set of combinations. So you try to solve your K, U. So this is for a given n, and this is for given n. So you compute this for this thing, and you obtain your solutions. The solutions, let us say, the solutions are U bar, uh, W bar. So then your U actually is again a combination of summation UN bar cos n theta and W is equal to summation. So you find solution of UN WN from the individual kind of FEM by solving each for a different n, and then you try to superimpose by multiplying with its basis vector cos n theta. Sorry, this one is cos n theta, and then if you add those all things by the principle of superposition by multiplying with its corresponding basis vector, you will get your final solution even in the cases when the loading is non-axisymmetric in nature. So this is how you try to deal with your non-axisymmetric loading in the case. And sometimes it is really worth going for dealing non-axisymmetric load in this manner, because sometimes the computation becomes too much expensive if you try to do it in 3D sense. However, here what you're doing is you may be solving 4 or 5 combinations, each one in a 2D sense, and superposing this 4 or 5 problems, because not all n will be active, or not all projections would be active for a given given loading conditions. If it is only dependent on certain basis, if it has only projection in certain basis, not all, you'll only try to find the solution in those for those projections and you try to superimpose them to get your final solution. So this is how you even deal with problems with the non-axisymmetric loading by projecting in this form. So this is how you solve non-axisymmetric loading by principle of superposition. So with this, what we'll do is we'll end today's class, and what happens is in the next formulation, which would be a new topic, and so we can have a new class to start with this. So at this point I will stop and I will check if you have